Hey there, ladies and gentlemen. Here we go. Second semester, jumping right into some algebra to prepare yourselves for the task of geometry ahead. And you're here because you want some more formal notes, maybe a little bit more explanation about rationalizing denominators and simplifying radicals. So here we go, off, and away. Let's begin. So the first question, the most pertinent question, I think we need to ask ourselves when we talk about reducing radicals, which is what I'm going to start with, is how do I actually reduce a radical and why does it work? So I'm actually going to start with the the why does it work. So the pertinent question I think I need to ask myself is why does or how excuse me why does a technique for simplifying radicals even exist? Okay. And that's a weird, kind of a weird way to ask that question, but the point being is that we if we have this technique that actually can simplify a radical, we have to lend some idea to why this technique is going to be a useful one, or at least a correct one. And so the way I can answer that question is to remind ourselves that the essential concept is that the square root of x is the same thing as x to the 1/2 power. So if we stretch ourselves to think of a root, root symbol, a radical symbol, as nothing more than a root exponent, then we're in business. Now, what I mean by that, and just to give you some idea, is that this is actually the second root of x, which is the 2 there is kind of implied. Unless you see a different number, then it's always going to default to being a 2. Third root is 3, fourth root, you see a fourth there. But it actually translates directly to this exponent. Now, you don't really need to know this till Algebra 2, but since you're here and you want a little extra, I'm going to go ahead and help you out. This top number, like the whole thing is called an exponent. Okay? The top number of the exponent is referred to as a power. The bottom number is referred to as a root. Together, they've actually formed the exponent. Okay? So you're actually always dealing with a fraction as a exponent, but most of the time, since you're never rooting the number, it becomes divided by 1. And since in this particular case, um, or in all cases of numbers, excuse me, division by 1 doesn't show up, so we drop it. Unless you're taking a root, it doesn't actually show up at all. So point being, whenever you're seeing a number to a square root, it actually does show up as a 2 in the bottom as opposed to a 1, meaning that you're not taking a root, which is why you hardly ever see it. And so this concept is important because if you accept the square root as a 1/2 power, that means then square root numbers, in particular square roots, have to play by the same rules as exponents. Okay, so that one in particular, that statement in itself isn't super important because there are lots of rules of exponents, but the one that's extremely important is distribution of powers. And I'm going to put distribution in quotation marks because it's not actually distribution. It just looks like at it. So the important one is the distribution of powers. Right? And what that actually looks like, as we continue our cavalcade of green, is that if you have two numbers, or more than two, in this case I'll limit it to two, taken to a common power, that's the same thing as taking that power and giving it to each individual factor. Okay? So it's important because if we accept the root as an exponent, and we know that we can distribute exponents among factors, that actually allows us to break apart a square root number um, for our benefit. So that leads us to the most important question, which is how do I apply the essential concept to simplify a radical? Okay. Well, what's important is that you realize that we're playing by number rules. And if we're playing by number rules, then everything is actually pretty easy to predict. So the underlying concept here is that, and let me draw a line so I can break these notes off nicely, is to accept that in most numbers, lies a perfect square factor and an imperfect square factor. Okay, so just a really quick note. When I talk about square factors, what I'm talking about are actually numbers that solve uh, as whole numbers and square roots. So square factors, numbers that solve as whole numbers under square roots. So for example, that would be like 1, 4, 9, 16, 25, 36, 49, 64, let's see, 81, 100, 121, 144. Let me keep going here. 169, etc., etc., etc. And just as a kind of a kind note, at this point in your lives, you guys should have those memorized out to at least 13. 13 is 169. Those are the ones that you encounter the most, and if you can memorize those, you could be doing yourselves a great big favor, okay? So this underlying concept, this guiding principle that in every single number lies a perfect square factor and an imperfect square factor, and this is in most numbers. In the cases that this doesn't actually occur, would actually probably be more than likely prime numbers, with a few extra exceptions scattered here and there. So this actually sets up a very easy methodology for us, because if we take the concepts that I've shown here in green and then apply the red concept, we actually have a nice methodology to simplify square roots. So for example, if I want you to simplify, oh, I don't know, let's just pick an easy one, square root of 40. We can actually break this off into very particular steps. So step 1 would actually be to check if it's already a perfect square. And at the same time, if it's prime. Because if it's a perfect square, it's automatically solvable. And if it's a prime number, it cannot be solved or cannot be simplified. Cannot be simplified.
If you are in charge of running the new teacher book fair, please contact the upper admin office at 38411. Thank you.
Okay. And that was from Mr. McCarthy. All right, so step 1 is to check for a perfect square or if it's a prime. And that's a step I think most of you guys figured out while working the worksheet today, that is going to give you a huge leg up, because sometimes you get one right off the bat that is automatically solvable, or you can tell right away can't be broken down. And again, it's not only prime numbers that cannot be simplified, it's just a common type, and that's what we should check off right off the bat. All right, so that leads us into step 2. You want to break down the number into factors. All right, so if you take this square root of 40.
If you are running the new teacher book fair, please call 38402. 38402.
Okay, so if you think about 40 as a number you're trying to break down, you think of this in terms of factors. And it's easiest in this case is to make a list. 1 times 40, we have 2 times 20. 3 doesn't work, but we do have 4 times 10. I'll see 5 times 8 would work. Let's see, we go. 6 doesn't work, 7, it got 8, and that rounds the horn. Now, what you're looking for in particular is the largest perfect square number. And the reason you're looking for that is because if you break this thing down into multiple pieces, The square root's the part that you can fix or you can solve. Perfect square is one you can solve, and the non-perfect is probably going to be left underneath the root. Okay. So you pick the largest perfect square number, and then that leads us into step 3, which is to rewrite as a product of roots. Okay, so here's what I mean. So in this step, I'm actually going to pick 4 and 10 because that provides the largest perfect square. 4 is a perfect square. In fact, it's the only perfect square listed on that chart. So 4 and 10 is going to be my choice. So if we acknowledge that the square root is really just a power, just an exponent, this actually turns into 40 to the 1/2 power. Okay, so if it's 40 to the 1/2 power, that actually does us no good. But if we rewrite 40 as a product of two numbers, 4 times 10 to the 1/2 power, that would actually allow us, using our green rules here, particularly the one about the distribution of powers, that would allow us to actually take this 1/2 and apply it separately to the two factors. So we can break this down to 4 times a half, or 4 to the 1/2 power, excuse me, times 10 to the 1/2 power. Now, this doesn't really do a ton of good, but step 5 of this process, or step 4, excuse me, of this process, is going to be to solve the perfect parts. Okay. So what I mean by that is that the 4 to the 1/2 power can be solved. The 10 to the 1/2 power cannot. 4 to the 1/2 power becomes 2. 10 remains under a square root, and that's actually going to be your final answer. Now you should always check in step 6. Oh, excuse me, not step 6, step 5. Whoa. You should always check in step 5, and you should ask yourself this question: what else can be done? And what I mean by that is, can I break down the square root of 10 anymore? Can I do anything with the 2? Are there other elements that I can combine or simplify or multiply, divide, subtract? Are those actually, is there anything else I can do, or is that basically it? In this case, it's actually it, and so you're actually done. So again, if we acknowledge that the square root is really just a 1/2 power, and therefore has to play by the same rules as powers do, if we consider a number like square root of 40, which isn't already a perfect square, uh, and break that down in terms of factors, that 1/2 power can be distributed individually to the two factors. One part being perfect, which means it is solvable under a square root, that's the 4, and the 10, which isn't, allows us to solve the 4 to the 1/2 power, leave the square root of 10 alone to our simplified value. Okay? So that actually is a rationalize. So that gives us the simplifying roots part. So now the question is, what does it mean, and how do you rationalize the denominator? So the question first is, what does it mean? Okay? Because that's what I'm asking you to do. So it kind of behooves us to make sure we're clear on that. Rationalize the denominator simply means to remove the square root that occurs in the denominator of a fraction. And you can make a note here as well that this is actually a simplifying rule. So if someone asks you to simplify your answer and you don't do this, you're not actually simple. The example I can provide for you would be something like this. Like, this is not okay. And the reason it's not okay is that you have a square root in the denominator. But there is a process of taking this answer and converting it into 2 square root of 3 over 3. And this is hunky-dory okay. And the reason it's okay is that there's no square root in the denominator. So if someone asks you to rationalize the denominator, all it really means is take away the square root. Now the good news is if you ask yourself the question, how do I do this? It's actually super simple. You rationalize denominators by multiplying by 0, or by 1, excuse me. Except that 1 has to be written as a fraction. Okay, so you multiply by 1 written as a fraction. The thing you have to acknowledge at this step is that any number divided by itself equals 1, where x can be anything, so where x belongs to all numbers. And don't get freaked out by that notation. This just means x can be anything. Okay, so that's the principle which we're working. So we can provide a quick example. So let's say I want you to rationalize 2 over square root of, I don't know, 6, okay? So the step we're going to take is to multiply by 1, choose 1 as a fraction involving the root. So that's a little confusing. Here's what I mean by that. So we're trying to rationalize 2 divided by the square root of 6. So I'm going to multiply by 1, but I'm going to write 1 as square root of 6 over the square root of 6. Doesn't change anything, but what that allows us to do is to multiply straight across and make that a square root of 6 squared. You can take note here that came as a result of that multiplication, and this will actually, the root and the power will cancel. Now cancel is such a vague phrase. The reason it actually works is because, remember, that square root can be written as a fraction. That is the actual power, so this actually can be rewritten as 6 to the 2 divided by 2 power, which is the same thing as 6 to the first power. Hence, nothing actually happens to it. That's why a root and a power actually cancel, quote unquote cancel, because they're both of 2. Right? So in the end, what this tells us is that on the top I'll have 2 over the square root of 6. On the bottom I just have a 6. Now, we're not necessarily done because there is an implied step 2. Check for further simplification. Meaning, I have 2 square root of 6 over 6, but I can actually do something with these guys, so I have to. 2 goes into 6 3 times, so I end up with square root of 6 over 3, which is your final answer. All right, so kind of going over this one again, if I want to rationalize the denominator, that means I have to take the root out of the denominator. The way I'm going to do that is to multiply by 1, but multiply by 1 in a very particular way. If on the bottom is square root of 6, I know if I multiply again, that's the same as squaring it. If I square it, the two things will actually cancel, leaving me just with a 6. Now, I'm not necessarily done because I have to check to see if anything else can happen. In this particular case, 2 over 6 reduces down to a third, which is what appears my final answer. So just like always, make sure you guys are writing your summary for these notes. And these notes will be the only notes you're allowed to use, say, on a test, all right? So that's what I have for you guys. I know it's a pretty long video, and I apologize, but hey, sometimes math takes time. All right, so that's me signing off. Thanks.